So I'm skipping a section. So the next thing on our list in the notes was going to be buffers, and we'll do that Wednesday. I want to talk about titration. So do you guys know what that word is? Have you heard the word titration before?
I've seen the labs.
Just from the labs. Okay, so this is a way to quantitatively determine something. So what's the difference between qualitative and quantitative?
Through experimentation rather than through numbers, like math.
No, there could be math in both. There's definitely almost certainly going to be math in the quant. When you hear that prefix quant, what comes to mind? Amount, quantity. So when you hear someone has done a quantitative analysis, they're determining the amounts of substances. Qualitative just means that you're saying if it's there or not. So somebody could say there's lead in your water, or somebody could say there's 58 parts per billion lead in your water. One of those two things. So this usually gets used in titrating the concentrations of acids and bases. Almost everybody who's taken a chemistry class, when they get to the acid-base part, you do an acid-base titration. But it's not just for acids and bases. I did, I don't know, 1,000 titrations for sodium. So we needed to make sure that the water in the steam system had no sodium or chlorides in them. So none of the salt water had made its way into the system, because if it did, I mean, we talked about this, the pipes would rupture and people would die in seconds. Like we wouldn't make it out of the room if there was a steam pipe leak in here. So we were constantly checking those. So it could be acid base or it doesn't need to be acid base. So in that case, we used whatever the sample was from the steam water drains, and then we used silver nitrate. And the reason we use silver nitrate is because when silver and chlorides touch each other, they form a white powder. So you can determine how much chloride is in the water by using a known concentration of silver nitrate, and then wait for the precipitate. Okay, so this is what the apparatus usually looks like. There's something called the burette. It's this tall, skinny tube. It looks like a really skinny graduated cylinder, or it kind of looks like those pipettes, the longer pipettes we use with the pipetters. There's a stopcock at the bottom, which just allows liquid to come out, and it's very fine adjustment. You can get like a quarter of a drop to come through, or you can get it to just stream. So what we're going to do is usually, since we're more concerned about acids, usually what happens is we make a base of known concentration and we add that to the burette. We've got an acid of unknown concentration, and we're trying to figure out what that acid's concentration is based off of what the base's concentration is and how much of it we use. This is really similar to the dilution equation. So what we're going to end up doing is we'll have this clear, colorless sodium hydroxide base in the burette. We're going to allow it to drain through into a clear, colorless acid. But we'll also have an indicator in there, and the indicator's name that we're going to use is called phenolphthalein. And phenolphthalein will turn pink when the pH goes from being acidic to being basic. So what we're going to try to do is make it so it's the faintest, lightest pink color you've ever seen. If it looks like Kool-Aid, you've gone too far. If it looks like a blush wine, you've gone too far. This person here that did this went way too far. We're looking, so what you're going to initially see is absolutely nothing. Okay, but the solution is they're going to run together and you won't see anything at all. And then you're going to see a little bit of pink, but you're going to have a stir bar magnet at the bottom of this. So what's happening is right at this spot right here, there's so much acid that is just hitting it that the concentration there has made so much base being run into it that right in that one spot, the pH is above 7. But as it spins itself out and mixes with the rest of the solution that's mostly acidic, the pink just disappears. And this is what we're looking for. We're looking for this color right here. The whole solution is barely pink. And this one over here, we've gone too far. So when we get to this spot, we can kind of slow down and then start adding drops a little bit more more slowly. That way we don't get to this, we just get to this. What I usually do is I make up one of these, this whole trial. Usually you do 3 trials and I usually do a 4th trial, and trial number 1 is how close is it? So I will basically just blow one, let it go all the way through, open it full bore. The stopcock is just constantly dumping, and I just wait. And so let's say it drains down to 25 milliliters of the sodium hydroxide have gone in, and it starts to turn pink. I just sit there and wait, and I just let it stream as fast as it wants to. And then once it's gone to that last one, I just turn it off. And okay, so this streamed down to like 28 and I'm past the endpoint. So what I'll do is for trials 1, 2, and 3, I'll stream it down to 26 as fast as it'll go, and then I'll turn it off, and then I'll slowly add solution to it. I wasn't paying attention years ago, and this lab isn't a long lab, and there was this group. I was like grading and not paying attention, and I realized, wait, I'm still here, and it's been over 2 hours. And this group is sitting there going, drop, and they're on their first trial. Drop from 50 milliliter mark. They've gone down like 30 milliliters, and they needed to get to like 36. So it was going to be another like 20 minutes before they even did their first one. And I'm just like, burn one. Don't even worry about it. Just blow it away. And so you know approximately where it is. Because sometimes bad things happen and you mess up your sodium hydroxide solution, and you might end up using like 2 burettes. So you definitely want to make sure you know where you need to stop. The burette itself is kind of like the Moore pipettes, and the Moore pipettes were the ones that you could drain from, say, 0 down to 10. But then if you let any fluid out below 10, you have no idea how much you put in. So these things are going to be marked. It'll probably say 0 milliliters up here, and it'll drain down to, and this will be 50. So you can't let it go past this. If it does, then you don't have any idea how much solution you put in down here. This should be able to give you at least certainly 1 decimal place, possibly 2 decimal places, because the marks are very close together. They're sort of like the milliliter marks on here. So this is what we're looking for. So there's a problem with using sodium hydroxide though. Sodium hydroxide, you guys have used it before, even in its solid form, and I've given you a warning about don't let any of the crystals like hit the table. You need to clean them up immediately. And the reason is because they don't have a set hydration number. So with we used copper 2 sulfate last quarter, and there's 5 water molecules to it once it's fully hydrated, and that's it. It can't go to 6. It won't be 4. It's going to be 5. With the iron 3 chloride, it's 6 H2Os. That's it. With table salt, it's 1 H2O. With potassium oxalate, it's 1. There isn't any more. With gypsum, with the wall stuff, the drywall, it's 2, and that's it. With sodium hydroxide, it's whatever it can get its hands on. It will absorb so much that will liquefy itself, which is seriously problematic if you're in like a human environment. So what this looks like is a drop of water, and what actually it is a drop of solution with a pH greater than 15. So people will like touch it, and then they'll touch their face, and they're like, "What am I burning?" Like, well, because you didn't clean up after yourself. That's really it. So the issue is when I take the sodium hydroxide out to weigh it, to figure out, so we're going to make a 0.1 molar solution. So I'm going to need, I don't know, let's say I need 3.2 grams of sodium hydroxide. As I'm taking it out of the container, it's absorbing moisture out of the air. If I put it on the scale, it's absorbing moisture out of the air. So I don't have an accurate mass because I don't know what its hydration level is. So what we do is we do our best. We close up the container, and then we make our solution, and then we have to use a standardization test. So we'll start this off with a standardization test with something called KHP. Let me pull that. I got that from the lab here. We'll back up one sec. This is what phenolphthalein looks like when it's in acidic solution. It's completely colorless. And then once you've added hydroxides to it, you change its conformation. Like this bond right here breaks, and then it starts absorbing colors to reflect pink. this light pink color. So as long as when you add acids back, then this will turn itself back into this. It's actually kind of cool. If you've got it pink, you can add acid to it and it'll go clear again. If you add base to it, it'll go back to being pink. It doesn't get stuck. Okay, so we're going to be using this stuff, KHP, which is potassium hydrogen phthalate. Phthalate is one of the polyatomic ions I didn't have you guys memorize, and this is its actual chemical formula. And the nice thing about this salt is it's not hygroscopic. It doesn't absorb moisture out of the air. So whatever its mass is, you know what its mass is. So what you're going to do is you're going to make some of this stuff, and then you're going to titrate this stuff. And then from that, you can back calculate what the sodium hydroxide's actual concentration is. If it's actually 0.1 or if it's 0.09 or if it's 0.11, some whatever it is. And then once you have that concentration of sodium hydroxide, then you can go and titrate your the actual thing that you're looking for. This is a titration curve. So what I have here is pH is going from 1 to 14, and I've got volume of base added. So imagine that you've got your setup, you're going to do your titration, and inside the flask, the Erlenmeyer flask down here, I've just got a pH sensor. So if there's some acid in here and I got a pH sensor in here, it's going to give you an acidic pH. So I don't know, like say 1, the pH is 1. As I add acid to it, the pH is going to base to it, it's going to slowly neutralize the acid and the pH is going to start to go up. And then all of a sudden it's going to skyrocket and then taper off again. So what's happening at this point right here, at this, what is called the equivalence point?
They neutralize each other.
Yeah, we're at that exact spot where I've got just salt. All the acid and base have neutralized themselves out. We're not really going to attain this. We're going to be like hopefully a drop or two past this, which will be fine. That won't affect your final answer, so it won't be a big deal. But the important part is that we go slow, because I mean, what's going to happen here is you could add several milliliters and really get not much of a change. But once you get right here, adding a half a milliliter is going to take you from like pH 4 to pH 12. So we want to be careful when we get near the equivalence point. Mathematically and graphically, does that equivalence point have a name that you guys remember? What's the difference between the curve on the way to the equivalence point as opposed to on the way away from the equivalence point, if I'm moving left to right?
Slope is increasing.
Increasing slope and decreasing slope, right? Can you talk about concavity before the equivalence point? Concave up. After the equivalence point, concave down. What happens if I take the derivative, or sorry, the integral of this? What's going to end up happening? Because what we're doing is we're measuring the slope of the line, right? And so we'd measure this, and the slope would be nominal all the way up to as we approach the dashed line, right? And then it's going to go up, and then it's going to be undefined, right? Because at the equivalence point, I'm dividing by 0, so it becomes undefined. And then it's going to come back down. So if I were to do calculus on this, what I'd end up seeing is it would be, something like this, and then it would skyrocket, and that's what we'd have. So the cool thing about if we were using the computer with this is we wouldn't have to like determine where the equivalence point is. We could just let the computer give us our spike, and then we would know. Okay, so this curve is really specific. This is a strong acid being titrated with a strong base. How do we know that from what we talked about on Wednesday?
Salt can't change the pH.
The salt can't change the pH, so that means the pH should be 7 at the equivalence point. If the pH is 7 at the equivalence point, that means I had a strong acid and a strong base. If I used a strong, if I don't have a strong acid or strong base, let's say I've got, which is what we're going to use today. This H is going to get neutralized and you're going to end up with CH3COO Na at the equivalence point. So there's my salt, sodium acetate. But this thing is soluble. We okay with that? Because it's a sodium and it's an acetate. So I've got CH3COO negatives floating around. And since this is a weak acid, when it runs into a water molecule, it's going to make itself again and leave behind hydroxides. So that's going to make the pH elevated. So at the equivalence point for if the acid is weak, it's going to look like this. So this is the point where all the acid had been neutralized by the base, but because the neutralization produced a salt from a weak acid, that anion will end up causing the pH to rise. So instead of it being at 7, I don't know, it's at 9 or something like that. And so that's what yours is going to look like. Not that you're going to be measuring the pH, but yours will be above that because we're using vinegar as our weak acid. What's up with this one? Can you tell me which acid this is? This actually can only apply to one acid.
Is it a strong acid?
Has to be. Why?
pH 7 on the first one.
So we're looking for a diatomic strong acid. There's only one. So this is sulfuric acid. So H2SO4. The first one pops off there and the pHs are the same. And then I end up with HSO4. And that's what this one is here. So I'm going to yank the second one off there. And the pH has got to be a lot higher because we're trying to now pull an H off of a negative ion. So trying to pull something positive off of something that's already negative, making it now -2, I'm going to need more OHs to do that. And so that's why, I mean, we're way up here, 12 or whatever, instead of way down at 7. So we're using phenolphthalein today. And here's the phenolphthalein one. So you can see the equivalence point is going to be somewhere here, except we're using a weak acid. So it's going to be somewhere up here. So somewhere between, you're going to get color shifts between 8 and 10. But what's the volume difference between 8 and 10? Basically, what I'm asking you is how much does this curve run between pH 8 and 10? It barely anything, right? We're talking like drops, half drops kind of situation. So that's what happens once I've neutralized the pH, it will rapidly rise. So these are just the phenolphthalein one, and then the equivalence point or change points for other indicators. We've got most of them go from yellow to blue, and we're using the one that goes from nothing to pink up to red. So depending on what you want to do, you can, check pHs based off of different concentrations. There's the phenolphthalein going from colorless to pink. How about this one?
Dropping acid in a base.
In my burette, I've got an acid, and in my Erlenmeyer flask, I've got a base. So this is the opposite. We're titrating a base with an acid. So that's why the pH is high, because I've got a base in the flask and I'm measuring the pH and I'm adding acid to it. And so the pH is going to come down. I'm going to hit the equivalence point at 7. So this would be a strong base being titrated by a strong acid. Now, why does this look so weird? We haven't talked about this. This is blood. So how could you be in danger of having your blood pH change? Your blood pH is pretty rigid. If it changes very much, you'll become immediately sick. Like you won't feel well. And if you're too far or you go too far in either direction, you'll just die. And the reason is because your proteins will denature. So those complicated structures, if they're in an acidic or basic environment, they simply cease to exist as their normal structure. Crack open an egg and dump some vinegar on it and see what happens. The white will coagulate in the same way as it looks when it gets heated. So it's like, it looks like you're cooking the egg, even though all you're doing is adding a weak acid to it. And what you're doing is you're messing the protein structure up. You're denaturing it. You're allowing it to unfold. So you don't want that to happen. Okay with that? So what is it that could happen to you that could make this occur? It's like eating 100 warheads ain't going to do it.
Acid straight in the bloodstream.
That acid or base straight to the bloodstream, but that would be difficult to do. Like if somebody, it reminds me of Terminator 2. Do you guys remember that movie?
With a lot of it.
That's Terminator 2. Yeah, the molten metal at the blast furnace in the middle of LA that doesn't exist. But whatever. Anyway, in that movie, the Sarah Connor's trying to get out, and her psychiatrist is there, and she literally pulls some cleaning solution in a syringe out, and then she jabs the needle into his carotid artery from the side, just like, and she just sits there with her thumb on the plunger. So tell me about that cleaning solution that she pulled out. Is it acidic or basic? It's very basic. It's a concentrated cleaning solution, and cleaning solutions are almost always basic. So just a little bit of that injected into this guy's bloodstream and he'd be dead for sure. So that's probably not going to happen to you. So what would be a different way to introduce something acidic or basic to the bloodstream? What's the easiest way to get something into your blood? You're doing it right now. Okay. I am too. Breathing, right? Those air sacs allow whatever is in the air in the lungs to enter into the bloodstream. So you want to scare the hell out of a firefighter, say that we're going to go fight a fire at a chemical plant or a fertilizer plant. Why? That means you're going to have chemicals in the air. You breathe those things in, they could incapacitate you with a single breath. If you were to breathe in something that's very acidic or very basic, you could pass out immediately. And if you're left in that environment, protein denaturing will kill you really quickly. So what you want to make sure is if you take a breath of something acidic or basic, that nothing happens to you. So what happened to my titration curve? My titration curve used to be like this. What does it mean when it's like this? Well, look at the x-axis. Let's talk about that question I had before. How much volume does it take to go from 8 to 10 on this curve?
No.
Almost nothing. How much volume does it take to go from, I don't know, 6 to 7? 40? Something like that. It's hard. Why are those gauged in 12 and a half units? That's just stupid.
38.5.
25? Yeah, okay. 38.5. So 38.5 milliliters to microliters, that's a huge difference, right? So what this is the blood trying to stop a change in pH. And we haven't talked about it yet. We will on Wednesday, but that's what a buffer does. A buffer takes changes and slows the change, modifies the change, makes sure the change doesn't happen quite as rapidly. In the same way, if you're, falling off of your motorcycle, the helmet buffers your head, right? It absorbs the blow. So this doesn't look like a normal pH curve because you're trying to stop the pH from changing. Or this one, there's nothing stopping it. So it goes like that change right there to that change right there is minimal volume wise, but very important pH wise. Yeah, so this is talking about you're adding all of this, and I'm getting not much change here. So the buffer is effective. I just threw this in at the end here because it's just us remembering how to name acids and bases. Okay.